Hello APC Mechanics students, today we'll solve the past paper of RQ 2021 set 2 exercise number 2. Then always remember that the object itself or the figure appears to be above the text. Okay, so don't look, whenever you're reading a text, don't look at the figures below, just look at the figure above. Now object A is a long, thin, uniform rod. This is important, which means that the center of mass is located geometrically at the center. This is the center of mass, is located at the geometrical center. The mass m and has a length to L. This is tricky because we're used to the fact that the rod is of length L. Now they're giving us to be to L. That's free to rotate about a pivot of negligible friction at its left end as shown above. Negligible friction, it means that we can use the conservation of energy. In part A, they're telling us using integral calculus derive an expression to show the inertia, rotational inertia IA of object A about the pivot is given by 4 over 3 ml square. Then in order to calculate the inertia IA, so you should remember the formula, which is given by integral of x squared dm. And remember that this is a bounded integral. We should perfectly set the boundaries and the origin. So the boundaries are position. The position might be positive or negative, and they are set based on the origin. The origin is always and forever in such type of cases. It's chosen to be the pivot itself, and we need to integrate over the whole mass over the position. So our initial position 0 and the final position would be 2L. Now here we have two variables x and m. We need to unify them, so this is done by utilizing the linear mass distribution. So let me write but the linear mass distribution lambda is given by dm divided by dx, which is basically uniform. We don't have lambda, however, because it's uniform, we can say that it's capital M divided by 2L. And in this case, if we're isolating for dm to unify the variables, then dm would be given by m divided by 2L multiplied by dx. Now we're ready to solve the integral. Then IA would be the bounded integral from 0 to 2L of x squared m divided by 2L multiplied by dx. Now m over 2L is a constant, can be dragged out, and that would be integral from 0 to 2L of x squared dx. Now x squared would be x cubed over 3 from 0 to 2L, and we need to compute this fractions once at 2L and once at 0. You can ignore the 0, that would be m divided by 2L, L, so 2L to the power 3 divided by 3, and that would be 8 over 2, which is 4, and L cube over L, that would be L square. Then the rotational inertia on the point A is given by 4 over 3 ml square. Okay, this is it for part A. Now here we have a text. We can look at the figure above. Object B of total mass m is formed by attaching two thin uniform identical rods of length L at right angle to each other. Object B is held in place as shown above. Express your answer in part B in terms of L. So because this object is of uniform mass distribution, then we expect that the center of mass for the first part would be located geometrically, which is here. So that's the center of mass for this part. And the center of mass for the other part would be located here geometrically at the center of the mass distribution, geometrical center. Now for part B, determine the following for the given coordinate system in the figure. In part I, the x coordinate of the center of mass of the object B. You know that we have two different ways in order to determine the position of the center of mass. If we're talking about mass distribution, we need to determine the position using integral. If we're talking about discrete points, we can use the average mass formula. Now here in this case, we can treat this object B as if two objects, and each object is represented by a point. So let me say this is G1. What are the coordinates of this point with respect to the origin? It is by L over 2 and L. And this object is of mass m over 2. Why? Because the total mass of the object is capital M, so half of it would be of mass m over 2. Why this is half of the mass? Because each part of the object is of length L and the mass distribution is the same. And the object 2 has the coordinates given by L as an abscissa and L over 2, and of mass given by m over 2. Now once we have designated each part of the body by a point, and we know the coordinates of the points and we know the mass, we can simply determine the x coordinate of the center of mass. So xcm, we start by the formula, which is m1 x1 plus m2 x2 divided by the total mass m1 plus m2. Now the mass of each point is given by m over 2. And the position of the first one, the abscissa, is given by L over 2, the other one is given by L. Now here we can cancel the masses, so that would be L over 4 plus L over 2 divided by half plus half, and here you can factor out L, 1 over 4 plus half, that would give us 3 over 4, and this is just equal to 1, so that would be 3 over 4L. Then the position of the center of mass, the x, is given by 3 over L. Now as for the y, if you notice that due to the symmetry in the problem, we will just do swapping between L over 2 and L. So we can directly say that the vertical position of the center of mass for this object is given by m1 y1 plus m2 y2 divided by m1 plus m2, which is m over 2 multiplied by L plus m over 2 multiplied by L over 2 divided by the total mass, which is m over 2 plus m over 2, and we would get the same perfect result, which is 3 over 4L. Then the vertical position of the center of mass will be given by 3 over 4L. And before we move on, let's interpret the position of the center of mass of this object. Then 3 over 4L by 3 over 4L, which means that the center of mass is located somewhere here. So let me erase everything and say that this object can be represented by a point which has the coordinates 3 over 4 L by 3 over 4 L, and the total mass is given by m. This would be good for us in order to study the dynamics of the system. Now they're telling us here object B has a rotational inertia of IB about its pivot. So now we have two rotational inertias for two objects. The first one is given by IA for this object, and we have IB for this object. Before I read the question, let me interpret each one. Both they have the same mass, which is capital M, and both they have the same length, which is basically L, and here L plus L, which is 2L, but angled. Now both of them has the same axis of rotation at the pivot. Now before I read the question, I can anticipate directly that they will ask me about the rotational inertia, since this quantity would be different because it's about not how much it's heavy and how much it's big, but it's about the mass distribution along about the pivot. And in this case, the rotational inertia of A is greater than that of B, because you can notice that for B, what happened that its more mass has been shifted toward the pivot. The center of mass is located here with respect to the pivot. Whereas here, the center of mass is located at a distance L. You can determine this distance and indeed check that it's less than L. If you do projection like this and try to find this distance from the pivot, you will notice that it is less than L. Then which means the rotational inertia of B is less than that of A, because the mass distribution on average is more closer to the pivot. And indeed in part C they're asking me to compare IB with IA. I would say less than, and my justification would go for, since on average the mass distribution for object B is closer to the pivot P. Compared for the object A. Then the rotational inertia of B. Rotational inertia of B through P is less than the rotational inertia of A through P. Now object B is released from rest and it begins to rotate about its pivot. Part D on the axis below sketch graphs of the magnitude of the angular acceleration alpha and the angular speed omega of object B as functions of time from the time it is released to the time its center of mass reaches its lowest point. And this is a classical question. Let me explain why. Now whether we're talking about the object A or object B, both objects can be represented by a dot having all the mass and swinging along the equilibrium position. And for very small oscillations, the type of motion would be oscillatory or harmonic motion. And we know that such type of motions are utilized by sine and cosine functions, which have the following forms. And because we're talking about the magnitude, so we can ignore the part which is down. Now here we have two types of concavities. That would be the first one and that would be the second one, which is exactly similar. So 2 would be here and that would be 1. Then if you're trying to plot alpha and omega, one of the curves, so alpha would either have the shape 1 or 2 and omega would either have the shape 1 or 2. And in order to do the perfect matching, we need to understand what's happening. When the object is going down, the speed is increasing. And in this case, the increasing shape would be 1. So omega goes for 1 and alpha would go for 2. And that would be always the case whenever we're trying to plot omega or alpha for a body which is freely rotating under the influence of gravity. So omega is going to be something like that, part of a trigonometric function which is concave downward, and alpha would be something like that. Now in part E, so we refer to the figure above, while object B rotates from the horizontal position down through the angle theta shown above, is the magnitude of the angular acceleration increasing, decreasing, or not changing? So now we know that it's decreasing, and this is always the case because we're going through the equilibrium position, and we know that at the equilibrium position the acceleration would momentarily vanish, and this is also apparent from the graph. But we need to provide an answer which is much more general, because we don't expect in the AP exam that they ask us some stuff that are very straightforward. And we need to explain this by understanding what's happening to the net torque provided on the system. Now, apart from this complicated shape of the object, let me assume that the center of mass at a certain instant occupy this position, and it makes a new angle theta which is different than this one with the horizontal. Then that would be the radial direction and that would be the tangential direction, and the only force that's producing torque is the pull of gravity. Now if this is the horizontal again, that would be the angle theta, that would be the angle pi by 2 minus theta. Because this is horizontal and this is vertical, they are perpendicular, then this is again theta. Now the torque provided by the pull of gravity is given by mg, and the distance here, whatever the distance here, it's r, and that would be a constant. What's varying here is the cosine or the sine of the angle, since we always project the pull of gravity or the force along the tangential, so that would be cosine theta. And here, when the center of mass get closer to the equilibrium, you can notice that the pull of gravity becomes, or it will, this line will be aligned more along the vertical, and theta would to pi by 2. And when theta varies from 0 to pi by 2, the cosine function decreases. So the net torque provided by the pull of the gravity decreases, which means the acceleration decreases. But this is very difficult to explain in text. However, there's something much more easier to say or to state, is that the torque, there's another definition of a torque which is related to the distance, which is the level arm, which is the perpendicular distance from the pivot to the center of mass, which is this distance. So another way to understand it, because cosine theta would give you this distance, then r multiplied by cosine theta, it depends on this distance, and we call this distance to be the lever arm. As the center of mass approaches its equilibrium position, this lever arm decreases, which means the torque would decrease. So here we can easily state that since the horizontal position of the center of mass of the object, let me say, is moving closer to the pivot, then the lever arm for the force of gravity is decreasing. So the magnitude of the angular acceleration decreases. And now finally the last part of this exercise, object B rotates through the position shown above. So it starts with the same initial position, then it will rotate to this final position. In part F, derive an expression for the angular speed of object B. When it is in the position shown above, express your answer in terms of m, l, I, b, and physical constants as appropriate. So now at this point we know that whenever we're talking about acceleration, we think of Newton's second law. Whenever we're talking about speed, even if we have the acceleration, it's easier to consider conservation of energy because the acceleration itself is variable. And here we're talking about angular speed, which is omega, not the linear speed. So we don't care about setting omega as v over r. Now, without taking into consideration much about what's happening for the center of mass, we can directly start our solution with setting the p level to be the final position of the center of mass. Then take the p level to be the horizontal, passing through the center of mass when the object is in the final position. Always try to start your exercise with the steps that can be easily set. And because this is a big law, let me start by stating apply conservation of energy. Then in this case, energy initial is equal to energy final. energy is about being kinetic and gravitational. Now, based on our choice, the final gravitational potential energy is 0, and I'm pretty sure somewhere in the exercise it has been stated that it's released from rest, otherwise they would have provided an initial speed. Now, the total mass of the object is given by m. This is important, gh. Now we will worry about h because it's important to set h correctly. And the final kinetic energy would be half. Now okay, it's good, it's given in terms of b, so ib. And omega square, we're interested in determining omega square. Remember that omega would have the following engineering structure, which is a coefficient multiplied by g divided by l. Here in this case, because ib it's not given in terms of m and l, so I would enter into the game, and we don't expect that it would be given in terms of g and l solely. Now we need to set h properly. What does h represent? H represents the vertical distance from the center of mass in the initial position to the p level. Now, according to this statement, they're telling us take the p level to be the horizontal passing through the center of mass when the object is in the final position. Now, if you recall properly, the center of mass of this object is located in this quarter. Then the center of mass is here. And that's L over 4. That would help us to set our P level, which is here. Now we need to find the initial position of the center of mass. It's not always horizontal, pay attention. The rod was something like that. The object, sorry. And the center of mass occupies this quarter, which is a distance also L over 4, because the vertical distance is 3L over 4. And we need, okay, let me again say that h is the distance from the P level to the initial position of the center of mass. This is the initial position of the center of mass, and we just need to measure the vertical distance. If this is L over 4 and this is L over 4 and the total length is L, so basically it's L over 2, then this h is L over 2. As you can see that h is always tricky, then mg L over 2 is equal to half ib omega square. Half cancels with half, and we're interested in determining omega square. Then omega square is given by mgl divided by ib, and in this case omega is given by the square root of mgl divided by ib. And as you can see here, because we need to express our answer in terms of ib, the structure given by omega, which is a radical coefficient g over l, breaks down. And that's it for me in this video, guys. See you soon in a new one.